Hi, this is Mr. Lemansky. This is lesson 5.3. We just finished a section on point-slope form, and we have a little extension to that lesson here. It's called arithmetic sequences as linear functions. Now you can see in the title, the first thing I guess we need to talk about is what does this term sequence mean? A sequence, it's an ordered list of numbers. The numbers in a sequence are called terms, so it's an ordered list of numbers. Now the next thing in the title is arithmetic sequence. So if a sequence is an ordered list of numbers, what's special about an arithmetic sequence? Well, an arithmetic sequence is a sequence where the difference between the consecutive terms is constant. Now, you might have to stop the video for a minute and think, what does this word difference mean? It means subtraction, right? So we're looking at an arithmetic sequence is where each of the numbers in the list, if we subtract, we ought to get the same amount. Here would be a simple example of an arithmetic sequence, like 1, 4, 7, 10, 13, 16. Do you notice how each of these numbers are 3 apart? So the difference, so in other words, if I subtract any 2 of these consecutive numbers, I get 3, like 16 minus 13 is 3, or 7 minus 4 is 3, or 10 minus 7 is 3. The common difference is 3. That's another vocabulary word that you'll see on page 309. The common difference. Arithmetic sequences have a common difference. Okay? So one of the things you're going to have to do in the assignment today is on page 310, 1 through 3, it would be to determine if a sequence is arithmetic. In other words, does it have a common sequence? Or a common, I misspoke, a common difference, I meant to say. All right? An arithmetic sequence always has the following form. It starts with a number. We take that number and add the difference. The next number would be that number plus twice the difference, and so on. Okay? Now this little a sub 1, it just means it's the first term. D stands for the common difference. Now remember, the common difference is that same amount or that difference that's consistent through the sequence. So in my previous example of 1, 4, 7, 10, 13, 16, a sub 1 would be the first term, and the difference would be 3. So I want to make sure that you understand that this statement here that I'm going to underline is producing this. Here's how. A sub 1 represents 1. If I take a sub 1, which is 1, and I add the difference, do you see how that's getting me 4, which is what I have here? And if I take a sub 1, which is 1, and I add twice the difference, wouldn't twice the difference be 2 times 3? Wouldn't that be 1 plus 6, which is 7, which is the next number? And then look at the third term here. A sub 1 is 1. If I add on 3 times the difference, which is 3, can you see how I'm getting 10 out of that? So hopefully that symbolism makes sense now. Okay, an arithmetic sequence always has that form. You're going to need to be able to determine if a sequence is arithmetic. All you need to do is check and see if the sequence has a common difference. For example, if I had the sequence negative 3, 2, 7, 12, 17, 22, I got to see, does this have a common difference? This sequence is an arithmetic sequence. Here's why. Look at 2 minus negative 3 is 5 apart. 7 minus 2, 5 apart. 12 minus 7, 5 apart. Do you notice how each of these are 5 apart? This is definitely an arithmetic. I should have put this sequence is an arithmetic sequence. Probably should have wrote that in. Okay, because the common difference is 5. Now, what would be the next two terms? Well, if I put 5 more, I'd have 27, and if I put 5 more, that'd be 32. That's why I have the next two terms would be 27 and 32. Okay? If there's a common difference, you have an arithmetic sequence. We're going to graph a sequence. That's another thing you're going to have to be able to do. If you look on page number 310 and you look at numbers 4 to 9, they're going to ask you to graph an arithmetic sequence. Here's how you do that. I'm going to make up a sequence so we don't just do one of the problems in the book because we didn't have a lot of book questions. Here's the sequence I'm going to make up. -3, -1, 1, 3, 5. It's an arithmetic sequence. Can you see how the common difference is always 2? Here's how you graph it. Common difference, I just said that was 2. You make a little table. The first position, the first number is -3, so that's what the position stands for. The first number is -3. So my first position is x, -3 is my y. The second position is -1. The third position number is 1. The fourth position number is 3, and the fifth position number is 5. So it's just like here's the first, second, third, fourth, and fifth number in the sequence, and you see how I kind of just made a little table out of that. That's what I did down here. All I need to do now is graph that. So let me graph it. 1, -3. 1, write 3 down. 2, -1. 3, 1. 4, 3. 5, 5. Now, you might be wondering, why am I doing this in this chapter? This chapter is about writing equations for linear functions. Well, here's why what we're doing in this little extension relates to that. Look carefully at this graph. Can you see that this graph is linear because it's creating a straight line graph? Okay? That's why this lesson pertains to what we're learning in chapter 5. Okay? When you have arithmetic sequences, they are linear. Straight line graph. There's one more thing you're going to need to be able to do, and it's numbers 10 to 15. We need to be able to write a rule for the nth term of the sequence. So let's figure out, how do we write a rule for an arithmetic sequence? Well, here's the first thing. If you look at the blue box on page 310, it shows you how to write the rule. Now, this is going to look kind of technical or maybe a little hard at first, but it really isn't that hard. Here's what you're going to see. This will impress your parents if you show them this. If you explain, hey, I know how to use this thing, they're going to be like, what the heck is that? Here's how you find the nth term in a sequence. The nth term of the sequence, so this is what this stands for, would equal, remember, a sub 1 meant the first term of the sequence, plus the number of terms in the sequence minus 1 times the common difference. Okay? Now, that looks kind of complicated. It'd probably be easier for me to explain it with a simple example. So let's see if this rule actually works. I'm going to use the graph from the previous slide. Remember, our sequence on that graph was -3, -1, 1, 3, 5. I want to see if this rule will correctly predict a number in the sequence. So I tell you what I'm going to do. I'm going to see what the fifth term in this sequence should be. So pretend, don't look at this for a minute. Let's just pretend we didn't know. Can you see here the fifth term? Let me write it on here. 1, 2, 3, 4, 5. The fifth term ought to be 5. Let's see if this rule works. The fifth term should equal the first term, which is -3, plus, I want 5 terms, so I would take 5 minus 1, times the difference. Now, can you see in this problem, the difference is always 2. That's why I plugged a 2 in for D. let's calculate this and see if it works out to 5. So I have negative 3 plus, there's 4 times 2, and that's negative 3 plus 8, and voila, there you go, you're getting 5. Now you might be wondering, well, why would I want to do that? Couldn't I just look at this real quick in my head and get 5? Yeah, you could if it's a short sequence, but what if I said to you, I want you to find the 100th term of that sequence? Are you actually going to count those all the way up to 100? And I would hope not, okay? Here's what I would want you to do. I would want you to take the rule. I want the 100th term. So, the 100th term, this is what this stands for, the 100th term of the sequence should equal the first term of the sequence, which remember, the first term was right here, it was negative 3, plus the 100th term minus 1 times, let me get that out of the way, times the common difference, and didn't we see that the common difference, it's right here, I'm circling it, it was 2. Well, let me calculate that out. I have negative 3 plus, that would be 99 times 2. That would be negative 3 plus 198. The 100th term of the sequence should equal 195, and that's a heck of a lot easier than me trying to actually count to the 100th term and figure it out in my head. That's what you're going to be doing and practicing on numbers 10 through 15 on page number 310. Okay, I think that's all I needed to get through on my video. This keeps it within 12 minutes. If we have questions, we can talk about it in class.